National Electrical Code Section 620.22 requires a separate branch circuit for car lights. This ensures the lighting is not affected by other electrical loads in the elevator system. The primary purpose of backup power for an elevator is to enable the safe evacuation of passengers in the event of a power outage. Car lighting is essential for the safe operation of an elevator, as it allows passengers to see the interior of the car and move around safely. Based on the code requirement and the importance of car lighting for passenger safety, it is recommended to provide a standby feed for car lighting. This standby feed can be provided by a generator or an uninterruptible power supply, also known as a UPS. The elevator drawings indicate a separate 120-volt feed for car light. This separate feed ensures that the car lighting is not affected by any other electrical issues in the elevator system. To ensure the safety and reliability of the elevator system, it is recommended to provide a standby feed for car lighting. This standby feed should be separate from the normal lighting panel to ensure that the car lighting remains functional even if the main power supply is lost. Consider the implications of not having standby power for car lighting. If the main power fails and the car lights go out, passengers could experience panic or disorientation, especially if they are prone to claustrophobia or anxiety. A loss of visibility could also increase the risk of trips and falls within the elevator car. The generator or UPS selected should be sized appropriately to handle the lighting load. Consult the lighting specifications to determine the total power consumption of all car lights. Add a safety margin to account for potential inrush currents or future expansion of the lighting system. A qualified electrician should perform the installation of the standby power system, adhering to all applicable codes and standards. The installation should include proper wiring, overcurrent protection, and grounding to ensure safe and reliable operation. Regular testing and maintenance of the standby power system are crucial to verify its functionality. Perform periodic load tests to ensure that the generator or UPS can adequately support the lighting load during a power outage. Replace batteries in the UPS as recommended by the manufacturer. Keep detailed records of all testing and maintenance activities. Consider adding additional safety features to the elevator car lighting system, such as emergency backup lights that automatically activate in the event of a power failure. These lights can provide supplementary illumination and reassurance to passengers. Evaluate the existing lighting system in the elevator car. If the lights are outdated or inefficient, consider upgrading to newer, energy-efficient LED fixtures. LED consume less power, have a longer lifespan, and provide better illumination compared to traditional incandescent or fluorescent lights. This can reduce the load on the standby power system and lower operating costs. Document all changes made to the elevator car lighting system, including wiring diagrams, component specifications, and testing results. This documentation will be helpful for future maintenance, troubleshooting, and code compliance. Consult with elevator manufacturers, electrical engineers, and code officials to ensure that the car lighting system meets all applicable requirements. Obtain necessary permits and inspections to ensure that the installation is performed safely and correctly. Train elevator maintenance personnel on the operation and maintenance of the car lighting system, including the standby power system. Ensure that they are familiar with troubleshooting procedures and emergency protocols. Conduct regular safety audits of the elevator system to identify potential hazards and ensure that all safety features are functioning properly. Pay close attention to the car lighting system and its standby power source. The presence of a standby feed can significantly enhance the safety and comfort of elevator passengers during power outages. The National Electrical Code, or NEC, provides guidelines for electrical installations, including elevators. Section 620 covers elevators, dumbwaiters, escalators, moving walks, platform lifts, and stairway chairlifts. This section addresses various aspects of elevator electrical systems, including power supply, wiring methods, grounding, and safety devices. It is essential to understand and comply with the relevant NEC requirements to ensure the safety and reliability of elevator installations. In addition to Section 620.22, Other sections of the NEC may also be relevant to elevator car lighting and standby power. For example, Section 700 addresses emergency systems, which may apply if the elevator is designated as part of an emergency egress route. Section 701 covers legally required standby systems, which may apply if the elevator is required to operate during certain types of power outages. The specific requirements for emergency and standby systems vary depending on the application and local codes. The selection of a generator or UPS for standby power depends on several factors, including the size of the lighting load, the duration of the expected power outage, and the available space and budget. Generators provide a longer runtime than UPS systems, but they require fuel storage and exhaust ventilation. UPS systems provide instantaneous power transfer, but they have a limited battery capacity. The choice between a generator and a UPS should be based on a thorough evaluation of the specific application requirements. When selecting a generator, consider the following factors: fuel type, power output, automatic transfer switch, or ATS, and noise level. Generators can be powered by gasoline, diesel, natural gas, or propane. Diesel generators are generally more fuel efficient and reliable than gasoline generators. The power output of the generator should be sufficient to handle the lighting load and any other essential equipment that needs to be powered during a power outage. An automatic transfer switch automatically switches the power source from the utility grid to the generator when a power outage occurs. The noise level of the generator should be considered, especially if the elevator is located in a noise-sensitive area. When selecting a UPS, consider the following factors: power capacity, runtime, battery type, and maintenance requirements. The power capacity of the UPS should be sufficient to handle the lighting load. The runtime of the UPS depends on the battery capacity and the power consumption of the lighting system. UPS systems typically use sealed lead-acid batteries or lithium-ion batteries. Sealed lead-acid batteries are less expensive but have a shorter lifespan than lithium-ion batteries. UPS systems require periodic maintenance such as battery replacement and testing. The installation of a standby power system for elevator car lighting should be performed by a qualified electrician in accordance with all applicable codes and standards. The installation should include proper wiring, overcurrent protection, grounding, and ventilation. The electrician should also perform a thorough inspection and testing of the system to ensure that it is functioning properly. Regular testing and maintenance of the standby power system are essential to ensure its reliability. The system should be tested at least monthly to verify that it is functioning properly. The batteries in the UPS should be replaced as recommended by the manufacturer. The generator should be serviced annually by a qualified technician. Detailed records of all testing and maintenance activities should be kept. Consider the impact of power quality on the elevator car lighting system. Power quality issues such as voltage sags, voltage swells, and harmonics can damage or reduce the lifespan of lighting components. To protect the lighting system from power quality problems, consider installing a power conditioner or surge suppressor. A power conditioner regulates the voltage and filters out noise and harmonics. A surge suppressor protects the lighting system from voltage spikes caused by lightning or other electrical disturbances. The design and installation of elevator electrical systems, including car lighting and standby power, should be performed by qualified professionals who have experience in this field. Elevator systems are complex and require specialized knowledge to ensure safety and reliability. Hiring qualified professionals can help to avoid costly mistakes and ensure that the system meets all applicable codes and standards. In conclusion, providing a standby feed for elevator car lighting is a critical safety measure that can enhance the safety and comfort of passengers during power outages. By following the recommendations outlined in this discussion and consulting with qualified professionals, you can ensure that the elevator car lighting system is safe, reliable, and code compliant. Remember to prioritize passenger safety and adhere to all applicable codes and standards when designing and installing elevator electrical systems. Regular maintenance and testing are also essential to ensure the continued reliability of the system. Consider the specific needs of the elevator and its passengers when selecting a standby power solution. Factors such as the frequency and duration of power outages, the age and condition of the existing lighting system, and the budget available for upgrades should all be taken into account. By carefully considering these factors, you can choose the most appropriate and cost-effective solution for your elevator. The 120-volt branch circuit feeding the lighting must be sized properly to handle the load. This includes calculating the total amperage draw of the lights and selecting conductors and overcurrent protection devices that are rated for that load. NEC Table 310.15b16 provides ampacity ratings for conductors based on their size and insulation type. Overcurrent protection devices, such as circuit breakers or fuses, are designed to protect the conductors from overloads and short circuits. The size of the overcurrent protection device should be selected based on the ampacity of the conductors. The 120-volt circuit will have a neutral, and an equipment grounding conductor must also be installed. Grounding helps to protect against electrical shock and to provide a path for fault current to flow back to the source. The equipment grounding conductor should be sized in accordance with NEC Table 250.122. The size of the equipment grounding conductor depends on the size of the overcurrent protection device protecting the circuit. All electrical connections should be made using approved methods and materials. Connections should be tight and secure to prevent overheating and arcing. Wire connectors should be properly sized and insulated. Conduit or other approved raceways should be used to protect the wiring from physical damage. The location of the standby power equipment should be carefully considered. The equipment should be located in a dry, well-ventilated area that is easily accessible for maintenance. The equipment should also be protected from physical damage and unauthorized access. Signage should be provided to identify the standby power equipment and to provide instructions for its operation. The signage should be clear and easy to read. Emergency contact information should also be provided. Regular inspections of the elevator car lighting system and the standby power system should be conducted. The inspection should be performed by a qualified electrician or elevator technician. The inspection should include a visual inspection of the wiring, connections, and equipment. The inspection should also include a functional test of the lighting system and the standby power system. Any deficiencies found during the inspection should be corrected promptly. The elevator car lighting system should be designed to provide adequate illumination for passengers. The lighting should be evenly distributed and should not create glare or shadows. The lighting should also be energy efficient. LED lighting is a good option for elevator car lighting because it is energy efficient and has a long lifespan. The lighting control should be easily accessible to passengers. The controls should be clearly labeled and easy to operate. The controls should also be vandal resistant. The elevator car lighting system should be designed to meet the requirements of the Americans with Disabilities Act, or ADA. The ADA requires that the lighting be adequate for people with disabilities. The ADA also requires that the controls be accessible to people with disabilities. The elevator car lighting system should be designed to be safe and reliable. The system should be designed to prevent electrical shock and fire. The system should also be designed to operate reliably in the event of a power outage. Proper maintenance of the elevator car lighting system is essential to ensure its safety and reliability. The lighting fixtures should be cleaned regularly. The lamps should be replaced as needed. The wiring and connections should be inspected regularly. The standby power system should be tested regularly. By following these guidelines, you can ensure that the elevator car lighting system is safe, reliable, and code compliant. You must also consider voltage drop when running long distances of wire from the MCC to the elevator. Voltage drop can cause the lights to dim and can also damage electrical equipment. To minimize voltage drop, use larger conductors. NEC Chapter 9, Table 8 provides the resistance values for conductors. The longer the distance, the more important this calculation is to provide adequate voltage to the lights. You can use a voltage drop calculator to assist with this calculation. Make sure to select the correct conductor material, length of run, conductor size, and current draw for the lights. Once you have this data, you can calculate the voltage drop and make sure it is within acceptable limits. Generally, a voltage drop of no more than 3% is considered acceptable for lighting circuits. If the voltage drop is too high, you will need to increase the size of the conductors or reduce the length of the run.